What I'd like to do in this video is describe how to set up coordinate systems for problems with pulleys. There are basically two methods. One was shown in class, and the other one is the one in your textbook by Halliday, Resnick, and Walker. Both methods are perfectly fine, but you have to choose one, understand it, and execute it properly. So the way I'll describe how to think about it is with this problem called the Atwood's machine, which is located here. And what it consists of is a pulley that is suspended from the ceiling, and there are two masses strung on each side of it. The two masses are connected by a string, and the string is wrapped over the pulley. And let's just say M2 is greater than M1. So the way you think about it is you have to start with a free body diagram. So here's the diagram for M1, and it's got a weight and a tension. And then here's the diagram for M2, and there's a weight and a tension. The tension is the same for massless strings. Okay, now what you have to do is think about how this whole thing will move. So let's say M1 accelerates upward. I'm going to make a little arrow for the acceleration. And because the M1 and M2 are connected by a string, their motions are coordinated. So if M1 is accelerated upward, let's say it's getting faster going upwards, then M2 will get faster going downwards. So I'm going to write a little acceleration vector. Now you have to put in a coordinate system. I'll make this in red. For the coordinate system, the left mass will have a coordinate y going upwards like that. And then you have to choose the proper coordinate system for the right mass. And the way I showed in class is that if you want to use the same value for A for both masses, you have to choose the coordinate system so that it matches what you chose on the left-hand side. So on the left, A and Y are parallel to each other, and on the right, you want to do the same thing. That forces the y-axis on the right-hand side to point downwards. Okay, now what you have to do is write the equations. So for the left-hand side, it's going to look like this. T minus M1G equals M1 times A. And on the right-hand side, you're going to get M2G minus T equals M2. And the acceleration is exactly the same thing as what you used on the left-hand side. Okay, this is the method shown in class. Now, there's another way you can do this, and this is the method shown in the book. It's also very common. Okay, and what it is you're going to start with the free body diagram. They look exactly the same as before. So here I go. And then you have to think about the accelerations. So if M1 goes up, M2 goes down. So this is exactly the same as before. And then you have to put in the coordinate systems. So I'm going to make the y-axis go up on the left. And what Halliday, Resnick, and Walker will do is it'll make the coordinate system go up on the right. And that is because having the y-axis point up is a very common thing to do. So now what you have to do is write the equations. So on the left, you're going to get T minus M1G equals M1A. That's exactly the same as what we had before. But on the right, the situation is different. You're going to get T minus M2G equals M2 times the acceleration in the y direction. But because now the acceleration vector points down, you have to write the AY as this. It's a minus A. So in the end, your equations come out equivalent whether you use method 1 or method 2. But what's a little bit more complex about method 2 is that you have to be careful with the value of the acceleration for the second mass. So choose the way you want, but make sure you can execute it correctly.